Here we have the straight line APB. Points A and B are given points on the line, so any two points will fully specify a line. Point P is an arbitrary point on the line. Its position vector is R. Notice that vector AP is pointing in the same direction as vector AB. If one vector points in the same direction as another vector, then that vector is a scalar multiple of the other vector. So in other words, vector AP is a scalar multiple of vector AB. So AP is equal to some real number times vector AB. Now actually for this picture here we can see that T is less than 1. AP looks like it's about a half vector AB. But of course T can be any real number. If T was 0, then AP would be 0. We wouldn't even have a vector. We just have this point. We'd have the 0 vector. If T is some positive number, then as T increases, vector AP will increase in magnitude. It keeps pointing in the same direction along this line as T keeps on increasing. Now if T is negative, then AP will be a negative scalar times vector AB. So AP will be pointing in the opposite direction. So we can generate all the points on the line in this direction to the left of point A. Notice that if we take vector A, which is this vector here, and add it onto vector AB, by the triangle law we get vector B. So that tells us that we can write vector AB as vector B minus vector A. We can do that for any vector. All we need is the position vector of the head minus the position vector of the tail of the vector. We can of course do the same thing for vector AP. We take the position vector of the head of vector AP, which is R, and subtract the position vector of the tail of vector AP. That's vector A. So we can write R minus A for vector AP, and that's equal to T times vector AB, which we can write as B minus A. So now we can generate our line using this formula here. R is the position vector of any point on the line. So the coordinates of any point on the line are x, y, z. Points A and B, and hence vectors A and B, are given. So we will know these. So all we have to do is just plug in real numbers for T to generate position vectors for points on this line. So T can be any real number. So for example, if T is equal to 0, then we get R equals A. This bit goes out. We have position vector of this point on the line. If T is equal to say 1, we will end up with A plus B minus A, which is B. We will have the position vector of this point, and so on. We can generate as many position vectors as we like. For this portion of the line between A and B, the values of T that generated are lying between 0 and 1, because we have remember T is a scalar multiple of AB, so we're scaling AB down, if you like, from 0 to AB. If T is greater than 1, then we're multiplying a number greater than 1 by vector AB, so we are increasing the magnitude of AB, so we're getting points on this part of the line. So this part of the line is generated by plugging in values of T greater than 1, and if we take values of T less than 1, or less than 0 I should say, we are going to get points on this part of the line, because then we are multiplying a negative number by vector AB, so we are reversing its direction. So A is fixed, so if we multiply a negative number by AB, we're going to get a vector pointing in a direction that's opposite to the direction of vector AB. If we minus a vector, we switch its direction. So we get points on this part of the line for T less than 0. So let's take an example. Now we need 2 points on the line. They were capital A and capital B, and the position vectors that correspond to them are little a and little b. So we need to be given little a and little b. So basically we have to get our line by combining the vectors to get b minus a. Well, that's straightforward. And we need to add in vector a here. That's 3i plus 2j. So now we can generate any position vector on the line by plugging in any number we like for t. We can write the vector 3i plus 2j as a column vector, and we can do the same for the vector 4i plus 3j. Here's another example. Now we're dealing with vectors with k components. Well, we need to get vector b minus a. We write b as a column vector, so that's 2, 1, minus 4. A as a column vector is 5, minus 2, 3. Subtract the corresponding components. To get vector b minus a, we can multiply that by the scalar t and add on vector a. Now let's consider the Cartesian form of the equation of a line. So in 3 dimensions, our given vector a has components a1, a2, a3. Vector b has components b1, b2, and b3. So we need to be given the position vectors of 2 points on the line. Vector r is a general point on the line. Well, vector r has its tail at the origin and its head at a point on the line. So x, y, z is any point on the line. So the equation of the line that connects these 3 points, the 2 given points and the general point on the line, is given by this here. So we just write down that for using column vectors. Here's b minus a. Well, we just take the entries of b, components of b, and subtract the corresponding components of a. So this is vector b minus a. Its tail is at the origin and its head is at the point of coordinates b1 minus a1, comma b2 minus a2, comma b3 minus a3. We can now get the relationship between x and t, y and t, and z and t. We can combine these 2 matrices. We can think of them as matrices. We can multiply the scalar t by each entry here, and since these 2 matrices have the same form, have the same size, that is 3 by 1, 3 rows, 1 column, we can add corresponding entries. So we add a1 onto t times b1 minus a1 to get this entry, then add t2 onto t times b2 minus a2, and then a3 onto t times b3 minus a3. So now we can compare x, y, z is a 3 by 1 matrix. This matrix that we just got is also a 3 by 1 matrix, 3 rows and just 1 column. So 2 matrices are equal if and only if corresponding entries are equal. So x must equal a1 plus t times b1 minus a1, and so on. So we get these 3 equations. Now we can make the subject t the subject of each of these 3 equations. So that's what's done here. And of course these 3 quantities are equal to the same thing, namely t, so they must be equal to each other. So we equate these 3 fractions and we have the Cartesian form of the equation of the line. So this equation does not involve t, it just involves the coordinates of a general point on the line, x, y and z. The a's and the b's are givens. The a's and the b's come from 2 given points on the line. 2 points is enough to fully specify a line. So if the point with coordinates x, y, z is on this line, then if we plug in the values for x, y and z, this should hold. These 3 fractions should be equal to each other. So let's take an example. Let's suppose we have the point 93 minus 2 and the point 45 minus 1. We have 2 points that fully specifies our line. So we call one of the points a1, a2, a3, and the other point b1, b2, b3. So we have x minus a1, well that's x minus 9 over b1 minus a1. That's 4 minus 9. Then we have y minus 3 over b2, which is 5, minus a2, which is 3, and that must equal z minus minus 2 over b3 minus a3. We can then do a little bit of simplifying. We can see that this general equation of a straight line makes sense if we plug each of these points into it. Like this point is on the line, so if we plug a1 in for x, a2 in for y, and a3 in for z, we will get 0 for each of these fractions. 0 equals 0 equals 0. That checks out. If we plug the second point in, we get b1 minus a1 over b1 minus a1. Well, that's 1. Here we're going to get b2 minus a2 over b2 minus a2. That's also 1. And finally, plugging b3 in here, we get 1. So you get 1 equals 1 equals 1. Now here's the vector equation of the line. So r is the position vector of any point on the line. So we need to write our 3 points as column vectors. Well, if we want to do it this way. So this is vector A. This corresponds to vector A. So that's 9, 3, minus 2. That's this here. And vector B is 4, 5, minus 1. So we have to get B minus A multiplied by T and add on A.